For years, James Webb has felt like the final word in space telescopes. Bigger mirror, deeper vision, images from the dawn of the universe. It gave humanity the sense that we had finally built the ultimate eye in space. But now NASA is preparing something that changes the game in a completely different way. Not by looking deeper at one tiny patch of sky, but by moving so wide and so fast that it can measure the shape of the universe itself. This new telescope is not here to replace Webb. It is here to expose everything Webb was never built to chase. The invisible mass holding galaxies together, the force pushing the universe apart, and the hidden 95% of reality we still cannot explain. And once it launches, astronomy may stop asking what one galaxy looks like and start asking what all of them are doing at once. On paper, NASA's new observatory does not look like the obvious successor to James Webb. Its mirror is 2.4 meters wide, the same class as Hubble, and much smaller than Webb's 6.5-meter mirror. If you only judge telescopes by mirror size, you might assume this is a step backward. But that is exactly the trap, because the real power of this telescope is not depth alone. It is scale. This observatory carries something Webb does not, a field of view around 100 times larger. That means one image can cover an enormous patch of sky that would take Webb around 100 separate pointings to photograph. One is a microscope. The other is a wide-angle cosmic survey machine. Webb can show you one galaxy in almost unbelievable detail. Roman can show you what billions of galaxies are doing across space and time. And that difference matters more than most people realize, because the biggest mysteries in cosmology cannot be solved one object at a time. If you want to understand dark matter, dark energy, and the structure of the universe on its largest scales, you need massive statistical power. You need huge samples. You need breadth. Roman was built for that. It is not trying to out-Webb Webb. It is doing something Webb was never meant to do. Here is the real reason this telescope matters so much. Everything humanity has ever touched, seen, breathed, built, or studied in ordinary matter accounts for only about 5% of the universe. The other 95% is dark matter and dark energy, invisible components that dominate reality, yet remain among the biggest unsolved problems in physics. Dark matter reveals itself because galaxies rotate too fast to be held together by visible matter alone. The stars at the edges should fly away, but they do not. Something unseen is providing extra gravity. Dark energy is even stranger. It appears to be driving the accelerated expansion of the universe itself, pushing space apart faster and faster over cosmic time. We know these things are real in the sense that their effects are measurable, but what they actually are remains deeply uncertain. That is where Roman becomes dangerous in the best scientific sense. It was engineered specifically to measure those invisible forces directly through their effects on light and structure, not just infer them loosely, but measure them at scale. Roman is not another pretty picture telescope. It is a machine designed to map what we cannot see by watching how it distorts everything else. Roman's greatest weapon is gravitational lensing. Einstein's general relativity tells us that mass bends spacetime, and light follows that curvature. So even if dark matter is invisible, its gravity still warps the light of galaxies behind it. Those galaxies end up looking slightly stretched, distorted, or correlated in shape, in ways they should not if no hidden mass were present. If you do that with a small sample, you get hints. If you do it with enough galaxies, you get a map. Roman will do it with roughly 2 billion galaxies. That is the leap. Previous surveys worked with tens of millions. Roman moves into a regime where the dark matter signal stops being subtle and starts becoming overwhelming. It will produce enormous three-dimensional maps of dark matter distribution across cosmological volumes. And while doing that, it will also measure the expansion history of the universe over around 10 billion years using supernovae and large-scale galaxy patterns. That means Roman is not just looking for where dark matter is. It is also testing whether dark energy behaves like Einstein's cosmological constant or whether something more exotic is going on. In other words, this telescope may tell us whether the universe's accelerated expansion is simple or whether it points to new physics waiting behind the curtain. As powerful as the Dark Universe mission is, it will not be the only thing Roman changes. At the same time, The telescope will monitor around 100 million stars in the galactic bulge, watching for microlensing events, tiny brightenings caused when a foreground object bends the light of a background star. And if that foreground object has a planet, the planet leaves its own secondary signature. This matters because microlensing finds planets that transit surveys like Kepler and TESS often miss, especially colder planets farther from their stars, the kind of worlds that more closely resemble the outer architecture of our own solar system. Roman is expected to discover thousands of these planets, giving us a much better picture of how common solar system-like planetary arrangements really are. But maybe the most exciting part is the thing astronomers always quietly know. The most important discoveries are usually the ones no one designed the telescope to find. Hubble did that. Webb did that. Roman almost certainly will too. Once you start surveying the sky at this scale, resolution, and cadence, something unexpected is guaranteed to appear. Strange transients, unusual lensing events, new classes of objects, and signals we do not yet have names for. Roman's official mission is to measure the invisible universe. Its unofficial mission is to surprise everyone.